All right, thank you for the introduction. So the main purpose of this talk is to address this topic that recently emerged, the convergence of HPC and big data, and the idea is to provide a storage-oriented perspective, and also to give some more details about one contribution that we have made within a project, an European project in this area called Big Storage. So in July 2015, the cover page of the CACM was looking like this. It was an issue dedicated to external computing and big data. And inside, we had an article by Jack Dongara and Daniel Reed that explains the motivations and challenges associated to such a convergence, which between these two areas, a topic that starts to be acknowledged as pretty strategic and important, mainly because, well, there are many. The debate is open and not everybody agrees, but there is the basic reason in favor of such a convergence, which is that basically both need each other. So big computations generate large amounts of data that need a lot of power to be analyzed, being, for instance, one example of such a reason. And the status, the main obstacle to this is that basically the programming models and the tools are in a divergent state today. So it's one of the problems. So let's say the issue has been acknowledged as important enough to be mentioned, for instance, in the White House National Strategic Computing Initiative. And it's also at the core of the work of international working group called BDEC, which involves major research agencies from the EU, US, Japan, and China, and recognized researchers from the HPC and big data areas. And a group that organizes a series of workshops discussing motivations and opportunities for such a convergence. And actually one overarching goal of this series of workshops is the co-design of a software architecture that addresses the challenges of both communities. You have seen a version of this picture in the talk given by Jean-Pierre Villot recently, maybe you're very familiar with it already. What we see in it actually is really the divergent state of the software in the big data community on the left side and the HPC community on the right side. So to put things simply, in the big data community, the hardware level, typically we have off-the-shelf commodity hardware. On the HPC community, we have higher-end hardware components with low latency networks, accelerators, GPUs, and so on. In the big data side, data is typically stored in HDFS and processed through MapReduce frameworks or frameworks that followed or that are derived from MapReduce with higher level libraries for machine learning, graph analytics, stream processing, and so on, everything in Java or Scala. And in the HPC community, we have mainly MPI programs with OpenNP written typically in C or C++ or Fortran. So pretty different software architectures. So one challenge is basically to address the convergence issue is to try to design a software system that meets the needs of both. So try to see where convergence can be achieved. And let's say that one opportunity, one catalyst for such a convergence can be seen also the emergence of data science, which has been seen, seen as a fourth paradigm for scientific discovery with a catalyst for research, compared by some researchers to Gutenberg's printing press, in the sense that the fact that we have so much data available at such a large scale, available for many communities, would accelerate research as it happened in the past. So in this context, even if this topic emerged very recently, actually a couple of years ago we started a European project called Big Storage, which was focusing on the convergence of storage abstractions for HPC systems and clouds, which is a way to look at this HPC big data convergence today, since clouds are basically a privileged infrastructure for big data processing. So within this project, we looked at ways of enable this convergence at the storage level. So these are partners of the consortium. Some of them are in the room. Now, for today, more specifically, let's say What I'm trying to discuss is how to imagine a new generation storage file system that would address the needs of both HPC and big data applications, because of course, despite the different needs that we might see on each side, there are very similar needs also, and the goal of such a convergence would be to allow the two communities to work together, to join forces for joint applications. So let me start with a typical HPC application, maybe one application that you are familiar with. And here you will see the link to the previous talk, because what you will probably have in mind thinking of storage is that you would rely on a file system, which typically has a POSIX semantics. And we can zoom on that. So basically, what do we mean by POSIX semantics? So in the main feature that we are looking for, typically is the ability to read and write data to individual files. But in addition to that, you have a large number of features like file hierarchies or permissions, many things that the application sometimes don't need, as Emmanuel said just before. So, but people still implement them. As Jean-Charles said just before, people still implement this because somehow there is a fear that the applications would not accept that such features would miss from the system. So they keep implementing them, but the storage systems has an overhead because of this. So what we can try to do, for instance, is to just focus on the essential features, for instance, just reading and writing, and to files. But in what follows, I would not say files, I would simply say objects, and more precisely, blobs, binary large objects, let's say, to focus on the fact that they are supposed to represent big objects. So typically, many applications today could use blobs instead of files with only minor modifications. Now, if we look what happens on the big data side, and if we consider that the picture as it looks today, if we look at big data applications like machine learning applications or data indexing or big data analytics, what those applications do for storage is that they rely typically on some more structured abstractions like key-value stores or database-like storage abstractions, and sometimes directly they use the file system. So there are several options, but if we look more closely, actually all of them use a file system in the end. And similarly to the HPC case, the POSIX semantics of this file system is often unnecessary. So we witness a similar situation to the one that we see on the HPC side, and probably a shift to blobs. So you might have guessed the hypothesis that we want to test here, which is that the convergence could be achieved through the usage of this blob abstraction. But of course, to validate this, some evaluation is needed in all cases, in the HPC area and also in the big data area. And what I'm going to do now is to focus on one such case where the big data application uses directly the file system, and of course, other steps are necessary to validate the idea for the other cases. So to take one example, one class of applications that are able to leverage raw uses blob storage are, for instance, those where you have a very large number of small objects that could, for instance, generated by sensor networks, that could be bundled and stored in a form of a single large object, saving the metadata overhead of, with respect to a scenario where you would save every object separately. So for this, for instance, the Mona Lisa monitoring system from the CERN ALICE experiment is an example. There are many problems related to this context, but for instance, if we focus on one in particular, the monitoring application here computes a lot of aggregates in real time concurrently, over 35,000 aggregates, to provide the scientists with some real-time insight of what's happening on thousands of servers that are scattered around the world. And to do so, of course, there are constraints related to performance, scalability, and concurrency. And we'll focus now on the concurrency problem, on the need for synchronization. One of the issues is how to handle synchronization, and more particularly, where to handle it. Why is this synchronization needed in this particular scenario? Basically, because computing aggregates basically means is a two-step process where you read an existing value and then you update it. So normally you solicit the file system several times, and you have plenty of processes that do that in parallel, and you want to do it efficiently at a large scale. So where can you handle such a concurrency? So one option would be to do it at the application level. So that would enable very fine-grained synchronization, but so you can use knowledge from the application to do things with a fine grain, but those optimizations that you do will have the risk to be very specific to your application. And on the other hand, this guarantees isolation of the various concurrent processes, but it doesn't necessarily guarantee anything when you have related operations in case of a failure, for instance. Another option would be to do this at the middleware level. And here again, you guarantee, we can guarantee isolation. There are no guarantees about the consistency of related operations on data, and no guarantees in case of failures. And and besides, you don't use knowledge from the application. And finally, there is a third option, and you will guess that this is the one that we are interested in, which is to place this synchronization layer at the level of a storage system and try to use the storage protocols to also handle synchronization. Let's say that this is our choice, and the idea is to use the notion of transactions at the level of the object store and use them for synchronization. So if you do have such a feature at the level of storage system, you don't need to handle the synchronization at a higher level. And this is what you gain. So application writing should be easier. That's the main idea. So that's the idea that was implemented in a prototype that is called Tier, which basically provides such lightweight built-in transactions at the storage level. Now, of course, you've already heard about transactional storage systems. So such systems exist already, and you might wonder why we need a new system of this kind. So why not just use what's there already? Well, actually, they are not really enough. So we can typically, in our context, we focus mainly on large objects that are chunked and distributed across many servers. And you need consistency guarantees, in particular atomicity, both for reading and for writing objects that can span across multiple servers. So many of the existing projects can allow such guarantees for writing, but not for reading. And that's something important. So this is why in this system, the idea was to map every read and write to transactions actually internally. So every read and every write is mapped internally by the storage system to a transaction. And it relies on some existing algorithms, a protocol called Orap. It implements lock-free writes. It leverages some well-known technologies from LevelDB, flat buffers, and others. So it is a real implementation that amounts to up to a bit more than 20,000 lines of C code right now. And we've done some testing, some initial testing with the Mona Lisa use case with real data. And the system was compared to some of the state-of-the-art storage systems. For instance, Rados, which is the object store used by the Ceph file system, which is pretty well known. The Azure storage blobs from the Microsoft cloud, and Blobsphere, which is another blob storage system developed at INRIA. So here are a couple of figures that I can show. So of course these are preliminary figures, so not, let's say it's just the beginning of the evaluation. So in this comparison, so you have concurrent writes, and we measure the average throughput while increasing the number of concurrent writers. So we compare these systems that I mentioned, and basically tier is the only one. The main point is here that you do concurrent writes, first of all, without synchronization. So the writes can overlap. Normally, if you want your application to be correct, you would implement some synchronization, but we don't do it here. At the application level, this is not needed when you use this transactional blob storage, because its concurrency is taken care of at the level of the storage system. For the other systems, it would be necessary, but we don't do it. If we accept, let's say, the incorrect results for the competitors, just to see how, just to compare the throughput. And we can see that actually tier has basically high performance compared to, it is comparable to Rados, but in addition, it provides the guarantees on the consistency of the concurrent writes. Now, if we add the synchronization for the competitors, which we would like to do if we want the application to be correct, in that case, it's clearer that such an approach based on transactional blobs can have a benefit, because you don't pay the cost of the synchronization at the application level. It's implemented more efficiently at the storage level. So those figures were for writes. We can see what happens for reads. Here again, there is let's say the performance is comparable with that of Rados. Actually, it's slightly lower than that of Rados, the object store of the Ceph file system, mainly because of the versioning mechanism that is used underneath to ensure that consistency for writing. And finally, well, I have two more pictures that I would like to show you. What we wanted to check also is to which extent this approach can ensure an isolation between readers and writers. So one of the ideas is that one of the features that you want is that if you have shared objects and you have writers and readers to the same objects, they shouldn't interfere. You don't want to feel the impact of the others, of the actions of the others. So if we look at the tiers bars here, which are the highest, here what is represented is the average throughput. First of all, we can see that it's pretty stable. So what we vary here is the proportion between readers and writers, starting with 95% reads, 5% writes, and to the opposite. So we try different combinations, and actually we see that the average throughput doesn't change when you change the proportions. And it is the case for tier, which pretty high throughput, and it's also the case for blobs here, so another system. For the others, we can see that the curves are going down, which is an indication that well, this approach could work. Of course, it has to be evaluated at larger scales, and in terms of scale, I was just mentioning that. Here is a test for horizontal scalability. So here we have a mixture of a typical 65% read, 35% write workload that is inspired by the Mona Lisa case. And we measure the average throughput, and we can see that it goes pretty well. So let's say these results, we consider them encouraging. So to wrap up on this presentation, what I showed here is how, let's say, big data applications, but one particular case of, let's say, data analytics, using blobs, transactional blobs, how it behaves. So it behaves pretty well. There are, of course, the other cases that should be tested with key-value stores and also in the HPC areas, area. So if you want more details about this, there is a paper published at Supercomputing last year, and I'm, of course, available to discuss and provide useful information.